Okay, so now we come to the interesting case where we are actually integrating over a 3+1 dimensional spacetime. And this is the result that we really want for the Euler-Lagrange equations. So to start off, just like we did in one dimension and in 3 dimensions, we are going to put the universe into a box. So because of that, time is going to run from minus t to t, capital T, and all of the spatial coordinates will be able to range from minus L to L. Now, I didn't tell you whether t is finite or not. I didn't tell you whether L is finite or not. So I very well might be in an infinite universe. In fact, for me in field theory, it is simplest to take both t and L to infinity. So I'm working in an infinitely big box. In this infinitely big box, it's perfectly reasonable to assume that all fields have dropped to 0 by the time you get to the boundary. Good. So we know, based on the examples that we've studied, that this integral is going to land up being an integral over the surface or boundary of the box. Our 3-dimensional box had 6 sides. How many sides does a 4-dimensional box have? Think about that. Pause the video and unpause when you have an answer. Okay, pause. Okay, good. Do you have an answer? Did you get 8 sides? That's absolutely correct. There are 8 sides to the box. So let's just write down what those different sides are. So first of all, we've got a side at t is equal to capital T, and x, y, and z are anything at all. And then there's going to be another side at t is equal to minus t, and x, y, and z are anything that you like at all. And one of the things that I would like to do when we write down these sides is that I want to write down what is the volume element on the surface of the box. So I'm going to write it like this, ds with an arrow, and let's discuss what that notation means. So first of all, I'm integrating over x, y, and z. So I'll have a dx, a dy, and a dz. But now I have to tell you the direction that I integrate over, okay? So let's imagine this is our box. I'm not going to draw the full 4-dimensional box. I'm only drawing for you the t direction and the x direction. And remember what we said. This volume element on the boundary of the box must always point outside the box. So over here at the t is equal to plus t surface, we must point in the t hat direction. So we will have a t hat sitting there. And at this other time boundary, we must point in the minus t hat direction. So we will have ds is equal to minus t hat dx, dy, dz. Good. Now, let me just make a few comments on what ds is. Actually, I've drawn a vector on top of it, which is maybe a bit misleading. It might make you think that we've got a 3 vector. We don't have a 3 vector. Remember now we're talking about 4 vectors. So, for example, when I write down ds is equal to t hat dx, dy, dz, actually, this is a 4 vector. The naught component of ds is just dx, dy, dz. And the 1 component of ds vanishes, as does the S2 component and the S3 component. The 1 component is for the x direction, 2 for y, and 3 for z. And this ds only has a projection along the time direction, so along the naught direction. For the second volume element that I've written down, ds naught would have been minus dx, dy, dz. ds1, ds2, and ds3 would again have vanished. Good. Okay, so that's 2 sides. We've got another 6 sides to go. So let's start with those. So we'll have another side at any t at x is equal to L at any y and any z. And also in the x direction, we'll have a side at x is equal to minus L and any y and any z. And for these, again, with my slightly sloppy notation for the volume elements on the surface of the box, we would have x hat dt, dy, dz. And here we would have a minus x hat dt, dy, dz. Then we will have a side at y is equal to L. Oh, sorry. I'm getting carried away. Good. X at y is equal to L and z. Another side at y is equal to minus L and z. And the volume elements for these two sides are as follows. So y hat dt, dx, dz, and minus y hat dt, dx, dz. And then finally, we've got a side at z is equal to L and another side at z is equal to minus L. And let's just write down the ds's. This will be a z hat dt, dx, dy, and a minus z hat dt, dx, dy. Good. Now, I want you to notice something. If we integrate over these two sides of the box, can you see that, well, integrating over these two sides of the box corresponds to integrating over a Euclidean space? Why? Because we're integrating over x, y, and z. So we're just integrating over R3 when we integrate over those two sides of the box. When we integrate over these 6 sides of the box, you see, these volume elements include dt. So we're actually integrating over a Lorentzian space with 1 time and 2 space directions. So 6 of the sides of this box include time, and 2 of the sides are just purely spatial. When the universe starts, at the initial time, you have a 3-dimensional space. And that's the space that we'll be integrating over when t is equal to minus t. When the universe ends at t is equal to plus t, again, we just have a purely spatial universe, and we will be integrating over the final spatial universe. And for any of the other 6 sides, well, we get to the spatial edge of the boundary, which includes time and 2 spatial directions. Good. We'll finish off the argument in a moment.